In this video, we're trying to find concentration of ions when we have a solution. So as an example, we can take a look at NaCl as a solution. So first of all, NaCl is an ionic compound. So it's made from an ionic lattice, which is made as from multiple positive and negative ions or cations or anions, like Na positive and Cl negative. And what happens to them is as soon as you place them in water, these ions are separated or dissociated from each other. And then each ion gets gets surrounded by water molecules. So this is the case. So let's say if you have NaCl, originally it's in the solid state. And then once it's dissolved in water, now it becomes aqueous. So aqueous, it means it's dissolved in water. So we show it with AQ. So anytime in chemistry you see the AQ symbol, you have to understand that that means it's just dissolved in water. And just so you know, this is a physical change. So it's nothing is really happening in terms of property-wise, chemical property-wise, in terms of for NaCl, basically. So it's just a physical change or a change of state. So it's going from a solid to aqueous right now. And eventually you can easily evaporate this water and you can get your crystals back. So you can get back your solid, ionic solid. So to further look at this, we can look at the dissociation equation. So dissociation equation is the equation that shows what exactly happens to this ionic compound once it's placed in water. So in the case of NaCl, because it's made from two ions of Na positive and Cl minus, and they all are exactly 1-to-1 ratio. So you end up getting one Na plus for every one Cl minus, and this is going to be the balanced equation for it. So as you can see, I'm also showing the aqueous sign for the ions as well on the right-hand side, because that means these ions are in water. So usually when you have a solution, the ions are also in the aqueous state as well. And let's say we have a concentration of 1.5 molar for NaCl after you dissolve it in water. So based on that and based on the stoichiometry between the two of them, now we can conclude that the concentration of Na plus is also 1.5 molar, and so is for Cl minus 1.5 as well. And the reason is because, again, for every one NaCl, you're ending up getting one Na positive and one Cl negative. So it's going to be based on the mole-to-mole ratio or stoichiometry, it's going to end up being the same exact number. So let's look at another example. Let's say we have 3 molar K2SO4 now. So first thing is we have to write the dissociation equation for that, which for K2SO4, we end up getting 2 K positives and an SO4 2 minus. So if the concentration of K2SO4 was 3 molar, then we can see the K plus has to be twice as more because of the fact that it has a coefficient of 2, meaning for every one K2SO4, there's two times the K plus produced. Basically, you have 2 K positives produced and only one SO4 2 minus produced. And then, so you can take a look at it over here. So K plus, there's 2 of them. And then SO4 2 minus is just one ion altogether. We call it a polyatomic anion, meaning it's a multiple atoms, which is having a charge of negative, and it stays always together, meaning S is always still connected to the other O's, and it doesn't break down into anything else. And there's only, the whole thing is just one of them. So just keep in mind that when you have something like K2SO4, a lot of people might think that K has to separate and then S has to separate and O has to separate. It doesn't work like that. And an ionic compound normally breaks down into one positive ion and one negative ion. By one, I mean like 2 parts, basically, something positive and something negative. So here it ends up being 2 K positives and then one SO4 2 minus. And based on the coefficients, again, we can understand that the concentration of some of them has to be the same, or for some of them, it's going to be double that. So take a look. Let's take a look at another example. So in this case, we're looking at 1 molar Al2O3. So first thing, again, we have to write the dissociation equation. So now we will see for every 1 aluminum oxide or Al2O3, we end up getting 2 aluminums with a charge of 3 plus, and then we get 3 oxygens with a charge of 2 minus. So therefore, if we have 1 molar Al2O3 to start with, the aluminum, because of the coefficient of 2, it has to give you twice as more concentration. So it's going to be 2 molar for aluminum 3 plus. And then for oxygen, the concentration will be 3 molar, basically. So 3 times as more as Al2O3. Just in terms of charges, if you get confused, you have to understand based on where they are in the periodic table, their charges are different. So sometimes you will find periodic tables that already has a charge of ions in them. So if you find them there, like if you find a table like that has the ions in it, it's perfect. If not, I have another video that later I will tag it, and you can find the charge of ions based on that. So generally speaking, in this case, aluminum is a metal group 3, so it has a charge of 3+ because it likes to lose all 3 valence electrons of itself. And oxygen, for example, is a non-metal in group 6. So it likes to gain 2 more electrons to become a charge of, to have a full shell. So therefore it gets a charge of 2-, meaning it likes to gain 2 electrons. So that's why aluminum, if it has a charge in an ionic compound, it's a charge of 3+, and oxygen is a charge of 2-. So the charges comes from there. But yeah, you can take a look at that video if you want to find out more. Okay, I hope this was helpful. Thanks for watching. And if you find it helpful, don't forget to subscribe. I'll put more videos later on. Thank you.